Okay, so this is going to be the last part of this lecture. Here I just want to go through what they call example 2 in this section in the textbook, which basically kind of runs through a bunch of different things we can say. You know, if we know the value of the lim sup of a sequence, then there are some things we can say about where the values of the sequence itself have to be, or at least where, you know, where we have to be able to find certain like infinite or finite collections of the values of the terms of the sequence. Okay. Before I get into that, I want to just state a corollary to the theorem I proved in the previous section, which is this corollary 12.3. So from the previous video, if the if limit of Sn plus 1 over Sn exists and equals L, then the limit of Sn to the 1 over n exists and equals L. So this is literally just because, you know, if this limit exists, then the lim sup of this sequence and the lim inf have to be equal. And that squeezes the lim sup and lim inf of this sequence, which have to be between, right? The lim sup and lim inf of the sequence of Sn to the 1 over n have to be in between the lim sup and the lim inf of this sequence. So if these two have, if this one has the same lim inf and lim sup, then this one does too. And that, we know that implies that this sequence has to converge. And of course, since they both have to equal the same number that these both equal, the limit here equals the same thing as the limit here. Or not necessarily a number, I guess it could be infinity or negative infinity. But yeah, anyway, so that's the corollary. So now let's get to the example here. So it has several parts. And the first one is this. So example, what they call example 2. It's really more of like sort of an assembly of facts. So they break it into 4 parts. So if L is the lim sup Sn, and you know, let's say it's not infinity. So I guess we can just say less than infinity. And alpha is a number greater than L, then we can say, right, the set of n for which Sn is greater than alpha is finite. If alpha is less than L, then they use kind of strange phrasing and notation here. I'm trying to clean it up a little bit. So then the set of n where Sn is greater than alpha is infinite necessarily. Okay, and so, right. So and then yeah, so that's basically what they state in part A, and I'll kind of describe why. They give an argument to show why this is true. I'm going to draw a picture here and then just kind of describe verbally why this has to be true. So let's see. So let's say this is L, okay? Now if alpha is over here, so what I'm saying is there are only finitely many terms, right? Because if there were infinitely many terms, okay, if there were infinitely many terms over here, then we would be able to find a subsequence of the original sequence Sn, which consisted only of those terms, right? And so then that sequence would clearly have, you know, we could find a convergent subsequence by just looking, you know, like either these terms, if they're unbounded, then clearly they go to infinity, and that contradicts the assumption that this is bounded. So if they are bounded, if the terms up here, if there are infinitely many terms over here which are bounded, then by the Bolzano-Weierstrass theorem, there's a subsequence which converges. So there would be some subsequential limit up here which is strictly bigger than L, and that we know is not allowed, right? So there can only be a finite number of terms bigger than the number alpha if alpha is strictly bigger than L. If alpha is over here, then what we're saying is there are infinitely many terms. And when I say terms, right, remember, I'm talking about the values or the indices n, right? This is actually the way of sort of counting up the terms, counting how many times the sequence ends up in a certain area on the number line, because there could be infinite repetitions of certain values. So it's possible that there are only like a few distinct different values that occur over here, but they might occur infinitely often. So when I say infinitely many terms, I really mean infinitely many indices n for which this is true, okay? So there have to be infinitely many terms here, because now if you think about this, right, if there were only finitely many terms up here, then by moving past all of those finite terms, all those finitely many terms in the sequence, which are above this alpha, then the rest of the terms after that point would all have to be less than or equal to alpha. But then clearly that would mean that the lim sup of the sequence would have to be strictly less than L, which is not good, right? If all of the terms of the sequence past a certain point are over here, then there's no way that this can be the lim sup, okay? So that's part A. So if you cut off above L, there are only finitely many terms. And if you sort of cut off below L, then there have to be infinitely many terms. So now part B, and I'll state it down here, I guess. The set of terms, or the set of indices for which Sn is greater than L itself, right? So we only talked about you know, cutoffs, or sort of like, yeah, bounds on the terms that are strictly greater or strictly less than L. But for L itself, it's actually ambiguous. It's possible that this set can be finite or infinite, right? An easy example of, you know, finite situation is where you take something like Sn equals 1 minus 1 over n, so that the terms approach from the left, right? Then this set has 0 elements in it, right? So then has 0 elements. For the infinite case, you can take Sn equals 1 over n, then it has oops. Then it has every you know, every term. All of the terms are greater than the lim sup, because the lim sup in this case is 0, right? Because the sequence converges to 0, right? So it can have any number, actually. It could have any finite number or infinite collection of terms can be greater than the lim sup itself. So it might be a little bit counterintuitive that, like, you could have a situation where there is an infinite collection of terms to the right of L, but if you look at any number, if you look at any actual number strictly to the right of L, there are only finitely many terms right of that number, right? But if you want to sort of understand that, just think about the case of Sn equals 1 over n. For Sn equals 1 over n, there's an infinite number of terms that are greater than 0, but there's only a finite number of terms that are greater than any given positive number. So like if I take, you know, 1 over 7,000, there are only like 7,000 terms which are bigger than that number, right? Or if I take 1 over 1,000,000, there are only 1,000,000 terms which are bigger than that number. but there are actually an infinite number of terms which are bigger than 0 itself, okay? So it's just something you have to get used to. So let's look at the next couple parts here. So part C here is basically just a mirrored version of part A. I'll state it, they use sort of different notation because they want to justify part C in terms of part A by using a kind of a mirroring argument. I'm just going to use the same notation, and I'm not really going, the justification is literally just like a mirrored version of the justification of A. So I'm just going to state it and then move on. And I'm going to change up the notation a bit. So sorry about that, but I want to keep consistent notation with what I was doing earlier. So if L is the lim inf of Sn and alpha is greater than L, then the set of n for which Sn is less than alpha is infinite. And the set, and then if alpha is less than L, then the set of n for which Sn is less than alpha is finite. And similarly, if alpha equals L, then the set can be either, right? So yeah, to just sort of draw the picture, if we have alpha over here, then what we're saying is there have to be kind of use this notation. So, or sort of, I don't know, sketch it this way. So there have to be infinitely many terms. And if alpha is over here, then there can only be finitely many terms. Okay? And yeah, again, L, you could have the sequence kind of approaching L from the left or from the right. So there could be an infinite number to the left of L, or only a finite number to the left of L. So it's ambiguous. So that's part C, and then the last one is just part D, which says that if lim inf less than lim sub, or actually in any case of Sn is less than or equal to the lim sub of Sn. You don't even have to require this strict inequality here, but it sort of makes the picture a little bit more vivid, I guess. It's possible the set of n where the sequence is between the lim inf and the lim sub is empty. In fact, it might be good exercise for you to just think a little bit about an example. Try to think of an example where this is true. If you want to do that, you can, feel free to pause the video. But so if you did that, well, here, I'll just give you the example. This is the example they use in the book, but something like Sn equals -1 to the n, 1 plus 1 over n, right? If you think about it, this sequence, it kind of approaches its lim inf and lim sup from the outside, right? So it's always bouncing back and forth between values which stay on the outside of this band. So the sequence is actually never in between its own lim inf and lim sup, right? Sorry, this picture is kind of bad, but yeah, it's never actually between its own lim inf and lim sup, which might be sort of a counterintuitive property. So anyway, that does it for this example, and that will be the end of lecture 7. Thank you, and see you in the next lecture.